Log on, tune in, find out. Another good idea from Cambridge.
Happy birthday, Stephen. It's truly a pleasure and honor to be here. So this is the question I would like to discuss. And this is, of course, one of the most basic questions of cosmology, whether or not the universe had a beginning. And much of what we know about this issue is due to Stephen's work. The question was first systematically addressed in the singularity theorems proved by Penrose and Hawking in the 1960s. They assumed a strong energy condition, which physically means that gravitational forces are attractive. And then they made some additional assumptions about the global structure of space-time, and they proved that spacetimes with such properties are past-geodesically incomplete, which means that there are some geodesics in the space-time which you cannot continue to infinite proper time in the past. And the interpretation of that was that this indicates that the universe has a beginning. The penultimate sentence in the book by Hawking and Ellis is, the results we have obtained support the idea that the universe began a finite time ago. So this actually proved to be a very fruitful approach to equate the beginning with past incompleteness. So the idea being that if you have some past incomplete geodesic, that means that your space-time has a boundary which is different from past infinity. And so that indicates that you need some boundary conditions, some new physics. So the universe, at least characterized by these conditions, should have a beginning. Of course, the beginning of the universe is associated with many perplexing questions, and there was no shortage of attempts to get around this kind of conclusion and to construct models which are actually without a beginning. And this is what I'm going to discuss today. Throughout my talk, I'll concentrate on semi-classical space-time, that is usual four-dimensional space-time continuum. So I'll discuss three candidate scenarios for how the universe could have no beginning. One is eternal inflation, then cyclic evolution of the universe, and what is called the emergent universe scenario, where the universe starts with some sort of a static seed. And to lift the suspense, I'll tell you my conclusion right away. That basically none of these approaches work. None of these approaches to try to avoid the beginning of the universe is successful, at least so far. The first two are actually necessarily geodesically incomplete, models of eternal inflation and cyclic models. And the emergent universe models, even though they can be geodesically complete, they suffer from a quantum instability which disqualifies them, as I'll explain. So let me discuss these three options one by one. First, eternal inflation. As Alan explained yesterday, inflation is generically eternal. So if you have, most of the models of inflation have this property. And in these models, you have pocket universes or bubbles nucleating and expanding in eternally inflating background. Since the universe in these models is eternal to the future, it's natural to ask whether or not it can also be eternal to the past. And that would, of course, be very nice, because it would resolve many issues that we have otherwise to face. Penrose-Hawking theorems do not directly apply to this case, because actually false vacuum that drives inflation is gravitationally repulsive. So it doesn't satisfy strong energy condition. So we need some other kind of theorems. Arvind Borde and I tried to extend Penrose-Hawking approach to inflationary models, and we actually were able to prove some theorems which were based on the weak energy condition. Weak energy condition physically means something different. It means that the local energy density is positive for all geodesic observers. And in the de Sitter space, in the false vacuum state, this condition is marginally satisfied, with this quantity being actually equal to 0. And again, with some global assumptions and using the global techniques of Penrose and Hawking, we were able to show that these space-times are past-geodesically incomplete. However, it turns out that this is not good enough. The reason is that even the weak energy condition is violated by quantum fluctuations. As I said, the weak energy condition is only marginally satisfied in the false vacuum state, and so quantum fluctuations naturally bring this quantity on the right to the negative side and violate the weak energy condition. You might think, okay, these are some unimportant rare events. However, these fluctuations are essential for the eternal nature of inflation, as it turns out. I will not get into the reasons why, but this is actually true. So a theorem which actually applies in this most general setting, where you don't have to, where you cannot assume basically any energy condition, is this theorem, kinematic incompleteness theorem. Actually, I should probably have said they are called singularity theorems, but maybe a better name would be incompleteness theorem, because the theorem doesn't really prove that there is a singularity somewhere. It just proves that you cannot continue your space-time beyond a certain region. So this kinematic incompleteness theorem that I proved with Arvind Borde, Alan Guth several years ago, very loosely stated, it says the following: that a space-time that is on average expanding, that is the average Hubble rate, is positive, is past-geodesically incomplete. I will give a more accurate statement in a moment. But the important thing about this theorem is that it is a purely geometric theorem. It doesn't assume any dynamics. That is, it doesn't rely on Einstein's equations. You could have some other theory based on some other equations. It also doesn't assume any energy conditions. Actually, both Alan and I mentioned this theorem when we were here 10 years ago at Stephen's 60th birthday. And from that, you can actually figure out the average time it takes to publish a paper when you write it with Alan Guth. Okay, so a more precise statement of the theorem. So first of all, I should say that an expansion is not really a property of space-time. It is a property of a congruence of geodesics in that space-time. And we say that a space-time is expanding if it can be filled with an expanding congruence of comoving test particles, that is geodesics. So let these black lines represent these expanding congruence of geodesics. And I want to consider some other geodesic observer different from these test particles who is moving through these test particles. Now, I want to denote h, the Hubble expansion rate of the congruence, in the direction of motion of the observer. I'm not assuming that the space-time is isotropic, so the expansion rate may be different in different directions. So that's why I specify the direction. And then the theorem statement, now with these definitions, is very simple. Is if the Hubble expansion rate averaged over this world line is positive, then the world line cannot be past-geodesically complete, cannot be complete to the past. The physical reason for this conclusion, actually the proof of the theorem is very elementary, and the physical reason for this conclusion is easy to understand. if you follow the geodesic to the future, then the velocity of the observer is redshifted relative to these particles, and the observer moves slower and slower relative to the congruence. But if you follow it to the past, the observer moves faster and faster. And what you can prove is that in a finite proper time of the observer, this observer reaches the speed of light relative to the congruence, beyond which you cannot extend the geodesic. So this tells you that that's where you reach the boundary of your region of space-time, and this happens in a finite proper time of the observer, so the space-time is geodesically incomplete. Now, it is an interesting thing that even though these geodesics of the congruence could be of infinite length, maybe they go all the way to past infinity, any other geodesic must be finite to the incomplete to the past. So this shows that that this space-time region must have a past boundary, and you can actually show that this geodesic reaches the past boundary in a pretty short proper time. So the corollary is that inflating spacetimes must be past geodesically incomplete, because inflation certainly is associated with expansion of the universe. And if the universe, you have this point in an inflating region, all the space-time to the past must also be inflating. And that indicates that inflationary universe must have a beginning.
Alex, I'm sorry. Does H average have to be bounded from below by a positive number, or it really could approach zero as you follow?
No, H can be negative or positive. All we require is that H averaged over.
Yeah, what I'm asking is whether H average has to be bounded from below by a positive number, or it's okay for it to slowly approach zero as you go backward, but that's still...
Well, if it slowly approaches zero, then the average will be zero, right? Okay, so now an interesting proposal to avoid this conclusion was made by these people, starting with Gear and Grattan. What they suggested is that even though for simplicity, talking about de Sitter space as a prototype of inflation, even though full de Sitter space cannot be filled by expanding congruence of geodesic, it has kind of the contracting and expanding parts, but half of de Sitter space can be. And so what they said, okay, what if the arrow of time is reversed in a half of de Sitter space? So you can do it this way with a null boundary between the two parts, or you can do it this way with a space-like boundary. And then you would have bubbles nucleating, kind of expanding in the upward direction in the upper half, and in the lower half you also can have inflation with bubbles kind of going upside down. Okay, this avoids, of course, the conclusion of the theorem, but here you have to impose some boundary condition at the surface where the arrow of time is reversed. And for me, this amounts pretty much to a beginning. So I think I'm done with my list of things here with eternal inflation. So I think the conclusion is that that inflationary universe, even though it is eternal to the future, should have some sort of a beginning in the past. Let me now turn to cyclic universes. And to quote Lemaitre, the solutions where the universe successively expands and contracts have an incontestable poetic charm and bring to mind the phoenix of the legend. Despite their charm, though, these models have some problems, which were first pointed out by Tolman in the 1930s. What he pointed out was that, okay, if the universe goes through cycles, and suppose these cycles are more or less periodic, then in each cycle, according to the second law, the entropy should grow. And so inevitably, the universe will reach the state of maximum entropy, and then that's where it will stay. And so this model, cyclic model, is certainly in contradiction with observations. Tolman himself pointed out how this can be avoided. He said that, okay, if in each cycle the volume of the universe grows, you will have a situation that even though the total entropy grows, the entropy density is bounded, and this is all we can observe. And so this is no problem. And this is actually exactly what happens in the cyclic models of Steinhardt and Turok. In these models, the cycles are not periodic cycles, but in each cycle the volume is increased. So you don't have this problem with the second law. However, if the volume grows, the average expansion rate must be positive. And it follows from the theorem that I just quoted that the space-time must be past incomplete. So this cannot be avoided. So a cyclic universe scenario must have a beginning in this sense. The space-time must have a past boundary. Okay, in the rest of this talk, I would like to discuss the emergent universe scenario, which has a pretty long and distinguished pedigree also, starting again with Eddington and Lemaitre in 1930s. For a while it was fell out of favor, but recently there was a lot of discussion of this kind of model. So in this scenario, it assumes that the universe starts out, or existed as a static seed. So a closed static universe which sits there forever, and then it starts expanding. There is an analog of this in Hindu tradition, which is called the cosmic egg. So they have this idea that there was a cosmic egg, which was again sitting there forever, and then it burst, and we have a universe. I guess this is what is illustrated in this picture on the conference website, but we should consult with organizers. So this scenario avoids the theorem because since the universe was static for infinite time, the average expansion rate is 0. And this model obviously is geodesically complete to the past. All geodesics kind of go back forever. Now, initially when I heard of this model, obviously when I first hear of this, it looks like it has some problems that it's very hard to surmount. For one thing, if the universe was sitting there forever, what triggers the expansion? This, however, a possible solution to this was suggested by Ellis and collaborators. They said that suppose we have, in this universe, we have a scalar field with a potential like this. For example, it can be a constant plus e to the phi. And then they start with the field phi, starts at minus infinity, with some constant phi dot. So this little ball just rolls forever along the plane with constant speed. And that just contributes a constant energy density to the static universe. So it remains static until phi reaches this regions where the potential rises up, and that's what triggers the change in the evolution. I'm not, by the way, saying that this model is particularly compelling. This is, I'm not making any value judgment about it, but my interest here is to see whether it is feasible in principle, and if it is, can this be a viable scenario for a universe without a beginning? Okay, once we have solved the trigger problem, so what Hindus needed was a scalar field for this thing. So once we solved this problem of a trigger, we have another problem, which is stability. We know that Einstein's universe, Einstein's static universe, is unstable, right? And here, however, stability can be enforced if we are, instead of Einstein universe had positive lambda and matter, dust, that is matter pressureless dust. Now you can have a stable static universe if you consider some exotic forms of matter, or if you consider modified models of gravity. And both of these scenarios were discussed by these authors. So I will not discuss modified gravity, I'll just consider some unusual matter. So suppose we have matter with equation of state P equals W rho with constant W and a cosmological constant lambda. So this is like similar to Einstein's universe. However, you can show that static stable models exist if you take lambda negative and this W in this range between -1 and -1/3. This value of range of W corresponds to repulsive gravity of matter, which means that if you compress this universe a little bit, density of matter grows, gravity becomes more repulsive, and it pushes it back. Now, if you increase the radius of the universe, negative lambda is attractive. Matter now is diluted, so lambda starts dominating, but lambda pushes it back. So it is a stable configuration with respect to radial perturbations, and it can be shown that actually for a range of class of models, it is stable with respect to any small perturbations, even in homogeneous. Okay. A particularly simple version of this model was discussed recently by the Stanford group, Graham and collaborators, where they took the value of W equal to -2/3, and then the density of matter is just lambda plus a constant divided by A, where A is the radius of the universe. A specific realization, physical realization of this model, you can think of this closed universe filled with a random network of domain walls. Then if you increase the radius of the universe, the walls are stretched, so the area grows like A squared, and the volume grows like A cubed, so the density is 1/A. Okay, so now if you write the Friedmann equation with this density of matter, it has a remarkably simple solution. The universe oscillates just as cosine omega t. And where I define this parameters, omega is simply related to lambda, and gamma is characterized as a relative density in this matter component and cosmological constant. So if you take gamma equal to 1, then this oscillating solution reduces to a static solution. And this is a stable static solution because obviously if you perturb it, it starts oscillating instead of running away. So this seems to be now a perfectly viable model. It is static, stable, and then you put in the scalar field that triggers change of behavior, so you have a universe without a beginning. However, I'm going to argue that this model has quantum mechanical instabilities. And this is based on my work with my graduate student, Audrey Mitani. So I'll do the quantum cosmology of this model in the mini-superspace approximation. So there's one degree of freedom, the radius of the universe, but I'll show that already at this level it exhibits an instability. So to do quantum mechanics, first you have to formulate to develop Hamiltonian formulation of your model. So this is the Hamiltonian for this kind of universe, where PA is the momentum conjugate to variable A. And this you can easily derive from Einstein-Hilbert action. And this U of A is this effective potential, which depends on the density of matter rho of A, which in our case is this. Okay? So very simple model. And the dynamics, all the dynamics is contained in the Hamiltonian constraint, which is h equal to 0. Now we turn to quantum theory. In the quantum theory, this model is described by the wave function, psi of A. And the momentum is replaced by differential operator. And the Hamiltonian constraint is replaced by this Wheeler-DeWitt equation. So this is the equation then, which looks like the equation for a particle in one dimension having zero energy and moving in a potential U of A given by this, where A plays the role of the coordinate of a particle. Sorry? What's the question? Here, 1 over A? What happened to 1 over A? It cancels out because this acts on the psi, right? This 1 over A. You can have, it depends on, you can talk about factor ordering ambiguity, but that is unimportant in the semi-classical case. Okay, if you're not satisfied, we can discuss this later, but I think there is no problem with this 1 over A. Okay, so this is the plot of the potential, U of A. Notice that you might have expected that if the solution is a simple harmonic, I mean, they call, by the way, this model simple harmonic universe because it has this oscillatory solution, and you might have expected that the potential would be that of a harmonic oscillator, but it isn't. The reason is that it has this oscillatory solution only when energy is equal to 0. If energy is non-zero, it has other solutions. So this is the potential, and it has turning points here and here. Since the energy is 0, total energy is 0, classical solutions can exist only in this range where the potential is negative. And so this oscillatory solution corresponds to a universe going back and forth between this A minus and then A plus. But looking at this potential, you can tell immediately that whenever the universe turns around at A minus, instead of going back to A plus, it can instead tunnel through the barrier and collapse to A equal to 0. You can easily calculate the semi-classical tunneling probability. It's just e to the minus 2s, where s is this WKB action, which in this model can be found explicitly in terms of elementary functions. And for a static universe, if gamma is equal to 0, equal to 1, then you have this very simple formula. So you can see that if lambda is very small in Planck units, the tunneling probability is extremely small. But nevertheless, this tunneling probability is finite. And this tells you that this kind of universe cannot have existed forever. And so it is not suitable for the starting point for emergent universe. I should mention this early work on oscillating universe models and semi-classical tunneling by Dabrowski and Larsen and Dabrowski. They considered more complicated models, so they couldn't obtain these simple kind of solutions, but much of what I'm saying here was anticipated in that work. Now, this is semi-classical approximation. It is interesting to see what actually happens if you solve the Borde-Guth equation. And it's interesting to contrast this situation with that of a harmonic oscillator. If you have harmonic oscillator, you have the Schrödinger equation, and then you impose boundary condition that psi should vanish at plus and minus infinity, and that determines the energy spectrum of the oscillator. Now, in our case, the energy eigenvalue is already known. It is fixed. It is equal to 0 in Borde-Guth equation. So we don't have the freedom to impose two boundary conditions. We can impose only one. And with this potential, we thought that the most natural boundary condition would be to require that wave function should vanish at A to infinity, right, when the universe gets infinitely large. And that's what we required. And this fully specifies the solution. Then you can solve the equation numerically. And here I illustrated some of the solutions with the wave function shown this in red for some values of the parameters. So in this classical allowed range, the wave function is oscillatory, as you might expect. Then it decreases exponentially at large A. But now at small a, it grows by magnitude. And this is not surprising, of course, because under the barrier, which is barely visible here, the wave function has two solutions. There are two solutions, one exponentially growing, one exponentially decreasing. And in the absence of boundary condition, generically, the exponentially growing solution towards 0 will dominate. And this is what we see. Similarly, for the static case where gamma is equal to 0, you might expect the wave function to be peaked where the classical solution sits, but no, it grows exponentially towards a equal to 0. So the fact that the wave function is non-zero at a equal to 0 indicates that there is a finite probability of collapse. Are we now down to 2?
Yeah. No, it's 4.
Okay. So now, can you avoid this? This is a simple model, the simple harmonic universe. You can consider more general models where in addition to this network of walls, you add other types of matter, like strings, dust, radiation, and so forth. You can show that this only increases the tunneling probability. In order to suppress quantum decay, what you need the potential such that it will grow at a equal to 0, and moreover, that it will, the integral in the WKB suppression factor should diverge. Then you would suppress the tunneling to a equal to 0. What this requires, as you can easily convince yourself, is a matter component with energy density like this, going like 1 over a to the n, with n greater or equal to 6. But more importantly, the Cn has to be negative. So you need a ghost type matter. And of course, ghosts have instabilities of their own, so this is not likely to be a solution to the stability problem of this kind of universe. Another thing that you could try is try to enforce that psi should vanish at a equal to 0. That approach was actually suggested by DeWitt in a different context. So let's impose the condition that psi equal to 0. You cannot impose it in general. However, you have these parameters in the model, lambda and rho 0, and you can fine-tune them so that the wave function vanishes at a equal to 0. And this can be done. Here is an illustration of such a solution. I think that, the philosophy could be, okay, maybe the universe should be such, the parameters of our universe should be such that these parameters should take such values as to ensure the existence of these non-singular solutions without a beginning. I suspect that this approach cannot be extended beyond mini-superspace. I don't have really a proof. It would be interesting to do a quantitative analysis of this. But the idea is basically this. You have a closed universe. If you add, suppose, some field there, right, which can have describing particles with different occupation numbers in the universe. Now, there is no conservation law to prevent the creation of pair, a particle-antiparticle pair in the universe, because the energy is 0 for a closed universe no matter how many pairs you have. And so I would expect that there will be transitions between these states with different occupation numbers of particles. So one kind of argument you can make is to say, okay, the more particles you have, the larger is the entropy. So I would expect this thing to drift in the direction of large occupation numbers and high entropy. But also you could say that in this situation, the solution for psi satisfying the boundary condition at infinity would generally be a superposition of these wave functions with different occupation numbers. You can fine-tune psi to be 0 at a equal to 0 for one of them, but not for all. Anyway, as I said, I don't have really a watertight argument. It would be good to have something more definite to say about this. So getting back to the question I asked at the beginning, whether did the universe have a beginning, my answer is probably yes. For all we know, there are no models at this time that provide a satisfactory model of universe without a beginning. Inflationary spacetimes are past incomplete. Cyclic spacetimes are either incomplete or lead to thermal death of the universe if you have oscillatory behavior. And emergent universe models suffer from quantum instability. Of course, if the universe had a beginning, it would be good to know what kind of beginning that was, what actually happened at the beginning of the universe. And these incompleteness theorem don't tell us anything about that. And here, apart from some minor differences in sign, I fully agree with Stephen that the most promising approach appears to be the quantum nucleation of the universe from nothing. Thank you.
Okay, questions, I guess.
Roger Penrose sent me a whole book, right, about his, I forget what he calls it, it's cyclic cosmology, but it would appear not to have a beginning. How does that fit in with this?
I think, for one thing, I would be happy to comment on that if I read the book. He didn't send his book to me, and he didn't publish. he didn't. But I think I heard his talk.
He sent it to me, but we're both in the same position with regard to reading it, so I think we should. Let's stop.
Okay, me. Here.
I believe that from logical point of view, you beautifully described this municipal space model in the third case. But you didn't try to do municipal space models or whatever by going backwards from inflation. You know, you showed incompleteness, but you should do quantum gravity there as well. And I'm not a friend of inflation, but the same is, I know that people criticize loop quantum gravity, but I think this is exactly what people around Abai say, that they go through singularity and they get inflationary region. So, you know, from logical point of view, I think that you treated these 3 points on different level.
Yes, well, but you see, in inflationary models, what my approach is that I follow the evolution of the universe back as far as I can using the semi-classical spacetime. This is perfectly justified when the universe is big compared to Planck scale, or there are other conditions. But then we find that we cannot follow anymore, and there it's not clear what happens. There probably quantum cosmology is called for. But I think just to show that the semi-classical, if you could have a model of the universe without a beginning, where the curvature is always much smaller than Planck scale, then we would never need quantum gravity, right?
I understand this point, but you know, there is this huge amount of work and review papers on quantum.
No shortage of work, right?
Wherever you go through singularity, I mean, people criticize it, of course, but I think one should mention it as well.
No, these models, by the way, these models of emergent universe, this work by Alice in particular, is based on loop quantum gravity. So at least this is what they say. I don't know much about this loop quantum gravity.
Okay, any other questions?
And Gary is there?
Can you pass the, can we should the mic, get the mic for, record it for posterity.
In many of these Wheeler-DeWitt treatments, the wave function is not normalizable, but I take it in the one you've just described it is. You can integrate all the way from a equals 0 out to infinity. And
You mean normalizable in the sense of psi squared?
yes, exactly.
I think here it is normalizable.
Right.
Yes.
Okay, so it actually makes sense.
Thank you.
Okay, well, maybe now that everything makes sense, let's thank our speaker again.